Perfect. So next speaker is Skvortsov from Australia, and he'll talk about methods of boundary homogenization and the problems of Laplacian transport. Please.
Good morning, everyone. The first statement is it's nice to be here, and it's very rewarding personally because words was used. I think Alexander used that word, that many different communities here, and we're trying to find the common language. And to present something after Sasha and Natasha is quite a challenge. So this is very elegant mathematics, and my talks will be from another part of the spectrum. Very practical, I would say. And I am a physicist by training, and I've been blamed very often that I cut corners. Happy to accept that, and that's who I am, and there is no rollback in life. Don't be harsh on what I'm presenting. Sometimes it's intuitive, but still we can explain our steps. Initially, when I thought I would be able to talk about Wiener-Hopf, I would become very enthusiastic, and I'll explain why very soon. But then I read what was done by David, what was done by, I would call it Manchester group, but because I know it's not Manchester, it's Sasha, Gennady, Anastasia. I should mention anyone. I know I missed someone, but I very soon realized that I will not be able to contribute much, and so I even will be talking something related to Wiener-Hopf, but there is a link, but no direct link. And decided instead present something which is related but not directly. So this is how we treat complex boundary in our practical research. Sometimes we ask to do something very promptly, sometimes we ask to do something very rapidly, not always politely. And I will tell that doing so, we're still trying to carry on some science, and there is some science behind, and some part of it, hope, will resonate with some part of this community. Okay, everyone knows what Laplace transport is. It is something, the equations related to Laplace operator, but then for some historical reason, people assume Laplace Laplace transport is about potential flow or electrostatics, nothing to do with that. Equation of viscous flow, unidirectional, is well known to be potential. And the next one, advection diffusion equation, I'm going to talk about that. So when you have drift and diffusion, you have advection diffusion equation. And that was initially topic of my discussion, because if you're talking about stochastic process, you have Langevin equation for the particle. Let's say I think about dust outside the window or fish in the ocean. I write a Langevin equation. From Langevin equation, I will write Fokker-Planck equation derived, and in steady state, I will have advection diffusion equation. So I effectively always have a drift and diffusion, and that is equation which is known Fokker-Planck or advection diffusion equation. What was coming new for me, and realization not from me, it's Martin Bazant, and that advection diffusion equation written in that form. So you have a passive tracer, you have a flow, and flow is potential. The nature of the flow doesn't really matter. It's maybe fluid dynamics, maybe electrical drift. These equations are conformally invariant, not being a Laplace equation. That was, for me, was a bit shock. So these equations are written here. Psi is potential of the flow, C is concentration of particles. They are conformally invariant, but they are not Laplace. They don't obey Laplace equation. So that something come out nowhere. So there is excellent review, and that's what I found the first from conformal mapping of some non-harmonic functions transport theory in published Proceeding Royal Society. And that I'm going to use heavily, and hope you will find something of interest and something maybe new. So if we consider two-dimensional case, we use a complex potential, we transform those equations to the top, then with the sample substitute, we can derive Helmholtz equation. So you have Helmholtz equation that you started something conformal invariant, and you can reformulate all problems you know in terms of that potential flow. For instance, a diffraction on semi-plate will be a transport equation for the semi-plate in the flow. Okay? Then I start looking for the papers of Gennady and Bazant and other people, and I found that there is a similarity effectively in physical graphic when you're talking about homogeneous model. You have parallel plates. You can translate to one problem to another. How good that translation is, we don't know, but definitely in terms of low frequency in their case, or I would say homogeneous model should be some similarity. And that's what we have been working for a while, how to have some complex boundary be replaced with some more plain boundaries, but using some rigorous mathematics, not just only saying we put about, and still have some solution. That solution may be primitive, but it is a solution. And yesterday, been many times people say we would like to have something to test. Yeah, that's probably. I am really happy to have Elena here because it's past her PhD when she was in Imperial, and PhD is available for download, and she published something with Darren Crowdy. It's effectively how to calculate the flow, viscous flow, along those arrays of infinite plates. I will use a pointer. So you have a flow in that direction, you have infinite plates, and this is exactly cracks in what previous papers of Gennady. And effectively, the main idea of those calculations is so-called, we call slippage length, sometimes it's blockage coefficient. So the effect of boundary, effectively in the far field, gives you some offset of the flow, and that is all, regardless of any complexity of the boundary. So all one parameter for the complexity of the boundary, if you move away here, is that offset. So it's become linear with the offset lambda. That is a point of calculation. The message is, if you know conformal map, it's from Elena's paper, then you can easily calculate that. You take z to infinity, it becomes very large, logarithm kills it, and it becomes linear, and what is left gives you that lambda. Okay? So whatever reason is probably historical reason, many people think infinite cracks or infinite plates. Doesn't need to be. Doesn't need to be. I'll show you that effectively that boundary can be calculated if you have Dirichlet here, Norman here boundary condition, finite height. Okay, so effectively you can have array of cracks. That's how it is, not infinite. You can have infinite array. It doesn't matter. So once you know lambda, then the problem is solved. The same problem can be solved with the Wiener-Hopf. The same problem can be solved with the Wiener-Hopf. And that was effectively Elena and Darren, they stated in their paper. And the problem can be solved with conformal mapping, or there is a relationship between Wiener-Hopf and that parameter lambda. So one or another. So you solve it independently, you validate. If you have approximate solution for the lambda, you have approximate factorization. That is the way to bypass it, to avoid that complexity. And that is what we are dealing with. We are trying to derive lambda by other simple ways. And I think I should mention another Cambridge fellow, Ernie Tuck, who was here many years ago, passed away. And I personally learned it from Paul Martin, and we published a number of papers on this topic. Okay? I'm extending what I just had before. If I have array of those, I use the same word, cracks, and it doesn't matter. They can be infinite or finite, and there is a period. And if I go far away from that boundary, I have a Dirichlet and normal, and far away, I have a Robin boundary condition, of course, because it's neither of them. And far away, the only parameter lambda, I use a delta here because they use divided by diffusivity. And you can derive just exact expression with conformal map, with our favorite, we mentioned many times. We mentioned elliptic functions, and elliptic functions here will be give you algebraic one in that case. You don't need to be equal, it must be periodical. You can have one is higher and now is lower, offset, without offset elliptic function, and that is calculated. Interesting thing for me, but I can explain it why, that lambda can change sign. Because if you have effective boundary condition, and if they are sort of Dirichlet, that boundary should be somewhere here. But if you have a reflective base, boundary should be here somewhere. It becomes negative, and becomes negative, and we do it numerical calculation by releasing particles, and it's found a very good result. So in that boundary condition, that parameter can have either side. So one way of thinking about the problem: first, you have regardless of any complexity, boundary can be simulated with the Robin boundary condition. Delta can be rigorously derived, but it can be positive and negative. That's what it is. So complexity may be geometrical complexity, or maybe complexity because of boundary conditions different, like Dirichlet norm. Okay, back to a simple example what we did. And someone asked us to calculate scattering, or I'm using about Laplace transport, still stick with Laplace transport, absorption of that absorber. If you ask a computational people to calculate absorption of that absorber, so you have a lot of discussion about how to have a deal with singularity near the edges, how you deal with your non-uniform mesh. But at the same time, if you go back to your conformal mapping, what you need to do, you need to calculate effectively conformal radius of that shape, and in the phi field, you map your solution to a cylinder. Calculation of conformal mapping is not conformal radius is not difficult, and that's what you have. B is the size of your I would say spike, and the A is the radius of your core, and you calculate it in general. So straight away from that result, if n is equal 0 and no core, you have a single cut. If you have n is equal to no core, you have cut of double length. You can have a cross. You can have a fish, and you have a cross section straight away. You don't need to solve anything to deal with any singularity, because you already calculated your conformal radius. You simply map your problem to the absorption by a disk, or by a disk, or by a cylinder, doesn't matter, by a cylinder, and that is done. So the same was if you have two cuts, or if you have two cuts, or whatever cuts how many cuts you have, all you need to do is your conformal radius. How do you know your conformal radius? So some people mistakenly think, oh, the same cross-sectional area. It's absolutely wrong, because this is zero cross-section area. You either simplest options to open a textbook, and there is a lot of results for different shapes, or you do it yourself, conformal mapping, and for piecewise you have Christopher Schwab's mapping, and all of this is easy to map. Back to Wiener-Hopf. If you have this geometry, infinite you have infinite domain, can be formulated as a Wiener-Hopf, of course, and you have a solution because it's from symmetry, and you can use it to validate. It has been published. Okay, now another one. Someone asked, we need to put some coating in a tube to maximize extraction of something from the flow. And you initially think, how would we do that? So you have a flow, you have absorbing stripes, and what would you do? Okay, for absorbing stripes, we have two-dimensional solution with conforming map. This is again signature of our elliptic function, and that is given as delta. And important point here, the stripe doesn't need to be narrow. For arbitrary stripes, it's exact solution, so you don't need to be narrow. You have all limited cases recovered. So we try this, we try that, but then what in Andrei's presentation, we simply use that shortcut and roll over and create a pipe. And we thought of spiral sort of distribution. And then we optimize the size of individual stripe and the period in order to maximize extraction from the flow. And this is results of our simulations. I assume that can be rigorously done, and the torus can be treated, but we haven't done it. Okay, more complex. So then, if you want to have different kind of boundaries, this is examples of what you need to do. You need to calculate that offset and conformal map equivalent boundaries. And you are working in a pipe, what you need to do, you need to have equivalent radius of the pipe will be a little bit reduced, but with conformal map, it's for viscous flow, you will do that. And that's what we've done. If we have very, very long stripes or whatever it is, or very, very long channels, what you can do, we can use a equation inside the channel and map solution with the solution up to here. It will be solution in individual periodic channel, and it is called in acquisition Lovett-Horn approximation, or it's a Fick approximation in diffusion. But eventually, what you need to do, you will need to come up with the equivalent pipe, and equivalent pipe gives you with equivalent conformal radius. Now we start talking a little bit about practical applications, and for a very long time we've been talking about how to apply this to problem of reducing drag. And for many people, everyone probably read about shark skin or dolphin skin effect, that y is reduced. It's not difficult to prove that you have in two-dimensional flow reducing drag in comparison with a flat surface, because effectively only spikes of your riblets will absorb the drag. And this becomes recently practical. Eventually, US decided to check whether it's true or not, and give money, including us. We must sort of DAPA, we'll give the reference to our sponsor, to Australia, Canada, and I think Australia, Canada, and US, and Penn State is going to test final results. So we need to produce effectively a design that will prove can reduce drag. You think about that, if you carry something from, say, Australia to Europe and you can reduce drag, it's probably for someone will be a shortcut to become rich, not for me. But it's effectively there is how to control flow around it. It's more important for us as well. Okay, there's some practical. Many people think, oh, it is something extraordinary, something what we can't understand. No, physics is very simple. The air is trapped between riblets, and that is why you have a mixed boundary condition, because if you have air, you have a stress-free boundary condition. No stress boundary condition is still no slip boundary condition in the riblet. So you have a problem with the mixed boundary condition straight away, and we need to homogenize somehow to effectively to derive effective parameters. Conformal map does it for you. Different design can be tried and evaluated. That's what we did. Many people did different design, and okay, now we come to the three-dimensional problem. So we need to have spikes. That's what Sasha presented. It's effectively individual pins, and that is more challenging problem. And that's I'm going to talk about next. The first translation to our initial two-dimensional results to three-dimensional results to have gaps in those riblets. When we have a gaps in the riblets, the problem becomes three-dimensional, but still you have no stress in the gaps and no slip on the riblet. So you have periodicity in that direction. And straight away give access to three-dimensional results. Okay, now we have a surface with the patches of mixed boundary conditions, and there is no conformal map, and we need to do something about it. And okay, we go back many years ago when the problem was solved first by Fock, who effectively conceptualized it in the following way. For one period of the lattice, he used a tube, and that is how you explain how you have hexagonal lattice, you have simplified model as a tube. Inside the tube, he had a diagram, and inside diagram, he has a patch of boundary conditions. He trying to find the solution inside the tube. It's not like we love tube. it is the way to progress analytically, to have something mixed boundary condition. Fock done very exceptional job in 1941. Second World War is coming. He produced, I think, 6 terms with unprecedented accuracy, nobody knows how, and published in the Proceedings of Russian Academy of Science. That was effectively used for a very long time, and much later, Leppington, he used another approximation. Then effectively that patch is large and very narrow around the edges, that approximation he used, and produced another result. And that one is related, of course, with conformal mapping I described before, because it becomes a two-dimensional solution. We effectively asked to evaluate complementary design. So when you flip one with another, so you have black one, say no stress, and another one no sleep, and people ask us what we flip in a complementary lattice, and no clear answer. But that machinery validated and VMatch2 allow us very quickly to access all range, not small range, all range of parameters and produce these results. So for a given fraction of or for a given fraction of superhydrophobic, we give a difference between design. That is given number. And we can optimize design for different patches, for different shapes, and that's really accessible. The last problem is related to that. When we have a tube, and inside the tube we have very complex blocking body. Very complex blocking body. As I said, the problem is for coaxial cylinders, and this is conformally invariant first. I'll show in a second why. The second one, the solution for the two coaxial cylinder doesn't imply that gap is small. It's valid for arbitrary two cylinders. It's exact solution. So we effectively what need to do, we need to find equivalent circle or cylinder that can be treated with the existing analytical solution. Okay, step one, you find using that ideas of conformal variance, but you still have drag associated with the front of this face of the cylinder. How would you treat that? Again, Robin type boundary condition. You need to impose Robin type boundary condition in two cross sections, and there is a fundamental known results that the Stokes drag is proportional of capacitance. You can prove it because monopole terms. So effectively, you need to have your terms, your faces with equal capacitance or whatever, and that's what we've done. And we really effectively what we can do. The longer the blocking body, the better treatment is, but shorter one is also treated very well because it's related to capacitance. We have two cases that can be treated analytically, and numerical results shown that effectively quite good approximations is up to AR of 0.5. Otherwise, console, mesh, or near the boundaries. Okay, now we're talking something slightly related to what Sasha presented. So we have all our pins, and on pins we have a Dirichlet boundary condition, and the base we have a normal boundary condition reflecting, and we're trying to find homogenized boundary, position of homogenized boundary. This is if that height of individual cylinder is 0, we go back to the problem I described before. But if it's not 0, then very interesting limit, because once I start coming to 0 radius, it becomes a singularity, and that becomes contribute much in comparison to two-dimensional case. We calculate that effective height of position effective boundaries for different limit rho is a ratio of radius for different age, and this is explicit formulas. And again, we use the same approach. Individual one, we put in a tube with reflecting boundaries, and we're trying to find effective position of effective surface here. For two-dimensional case, it's been validated extensively. We are in the process to create our favorite hedgehog, so a sphere with the reflective pins, and reflect that problem to reflection or absorption by a soft sphere. It is work in progress, but I think we are in a good shape. So effectively what you need to do, those pins will increase the radius, or depends on whether you're reflective or not base, of your sphere, and the position of effective boundaries can be anywhere. And if it's below the surface of the sphere, then you probably need to impose Robin boundary condition, because otherwise you need to impose your boundary condition outside your physical boundaries. This is our work in progress with Gennady, and I came with my own idea. Gennady sort of imposed the problem, and we start thinking about that problem related to been discussed before. So this is a very simple experiment and peel two properties, and two stripes, and Michael and it's been done so much for me. I was swarmed by amount how it's been done. I'm trying to find my way through that problem. We start talking, and no doubt that there are experiments where people done it recently. And what we are trying to do, we're trying to come up with a sort of model that describes the moving of that front with the feedback behind the front. And I'll show you some ideas I was initially thought would be fruitful, but okay. So there is no well-known model of so-called Frankel contour, and this is a position of the minimum of potential mass in springs, and that model is reduced to the well-known Singh-Gordon equation that has a many favorite solution well-known. If amplitude is small, the Klein-Gordon solution, that is what is required. And physicists have a special name for that phenomena. So when we have a broken link here, or slightly broken, they call the phenomena is called softening of optical modes. That's what they call it. And there are a lot of efforts to do that, what's happening in that softening of optical modes. And there is a well-known phenomenon of Pokrovsky transition. So it's very difficult to go there. My idea was, guys, if you have so nice solution for nonlinear equation in that case, and we're interested in a linear solution in that case, why not to use it to validate it physical relevance and low frequency in low amplitude limit. And the Frankel contour model was derived for two interacting plates and the sort of mass and springs in different plates. And if you start cutting randomly connection between plates, you can do that. Why would you start using nonlinearity from original linear system? It is the same. We add a little bit damping in order to have relevant solution for ideal system. Because solution in a sense of so-called shock waves or kink, anti-kink is very probably simplest one in nonlinear science. And so you have two parameters, because nonlinear system you have amplitude and velocity linked to each other. But if you map it back to Wiener-Hopf, it gives you velocity. It gives you velocity. So effectively, velocity only. There is an interesting avenue to do that cross-validation. I recently been publications in related system in nonlinear case, and once equations U is effectively misalignment of position of individual mass with respect to the minimum of potential. So once you have a shock wave solution, it means that next one is missing its place. And this is a defect in the system, effectively, or you can treat it as a, but this is idea was to use that solution Sasha was talking about and map it back to the Frankel contour. I don't know how successful or not we can be, and this is what effectively was reported by Sasha. So you cut all links and you have still Frankel contour. You can sum links, and this is a defect how it looks in that system. Because you have sign here, you have solution 2 pi, 4 pi, n pi, and so devil stairs. And that is, we are in process of doing and validating. Thank you very much for your attention.
Thank you very much, Alex. Other questions?
Alex, can you comment on this sign of when you discussed about this Robin condition? You told that the sign may be positive and negative, and from my experience, it should be negative, then
okay. I comment on that. I probably need to write something. So layer, you have C plus, C minus. What's the current? You have C plus minus C minus divided by D. It is your current. So if that one is fully reflective, and then now I start doing something fancy with that bond surface. So I effectively change my D by adding that lambda. But if my base is reflective initially, so my initial boundary condition was at infinity, because it was reflective. There is no, and as I'm doing something fancy, that boundary is moving up, and eventually will be somewhere here. So it goes through zero. If initially was a boundary condition reflective of Newman boundary condition on the bottom surface.
Thank you. Yes, please.
Yeah.
Very quick question. On your two last slides, there is where you have nonlinear wave equation.
Yes, yes.
What is the meaning of omega?
Omega, it is stiffness between layers.
All right.
That omega is stiffness between layers.
Because usually it's notation used for frequency.
No.
This threw me off. I couldn't.
Okay, foundation.
Gordon, right?
Yeah, Sanger.
What exactly, what solutions? Indeed, as you
King.
said, there are many solutions, no. But which solutions are relevant for your?
I think king, quanti-king, whatever it is, only.
But not multi-soliton, no?
If we go that path, that it is, these people, this is multi-soliton solution. This is multi-soliton solution. So you have each one defect will correspond to one soliton. Effectively, if I start with u is equal 6 pi, it means I have 3 defects, 3 soliton solution.
What about periodic solution?
Should be investigated. I mentioned it's work in progress, but yes.
No, there are no, again,
There are no elliptic for your favorite elliptic functions. We're trying to make a relevance similar to shock waves, sort of Burgers equation and shock waves. This is
there are also this symmetry reduction, Pinley equations, so there are.
I know I opened Pandora box. I'm well aware of that, and but we're trying to be practical.
Pandora's box is something with the coffee break.
With Gennady, I can mention last year Gennady sent me with that Hinchcock to Beltrami operator and to work with Beltrami operator. I tried and I found myself in a point of no return.
All right, great. Well, thank you very much, Alex.